The majority's overall conviction among specialists is that the hypothesis of how things came to be remains the major explanation for the beginning of the universe. This theory encompasses the advancement of stars, planets, and the question, what's next for life on those planets, including ourselves? Despite its odd name, the Big Bang provides an enlightening appraisal of what might have happened at the very beginning. The universe was once densely packed into a very small area, more tightly than a pinhead. From that moment, a massive release of matter and energy occurred, known as the Big Bang. That event, which happened billions of years ago, initiated the ongoing expansion of the cosmos. However, history, based on scientific data, has started to raise some oddities, and skepticism about the theory is justified. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever, researchers hoped its findings would substantiate the Big Bang theory regarding the origin of the universe. Tragically, or perhaps fortunately for scientific progress, after just a single year in space, the telescope astounded specialists with its ability to peer so deeply into the universe's past. The incredible capabilities of the James Webb Telescope have uncovered countless galaxies, going as far back as a time so ancient that it challenges our understanding of the universe's origins. This revelation has sparked a comprehensive reevaluation of what may have existed before the Big Bang. One significant moment came when cosmologist Rohan Naidu, working with data from the telescope, suddenly discovered a galaxy that formed just a few days after the Big Bang, making it the most distant universe ever seen. Naidu's discovery sent shockwaves through the scientific community, highlighting the astonishing capabilities of the James Webb Telescope and its immense potential to reshape our perspective on the universe. And this is only the beginning. The telescope promises to uncover astounding insights into the earliest periods of the universe's existence, a time barely studied before, yet one that holds the key to understanding the development of the first stars and galaxies. The telescope's discoveries have conflicted with leading theories, revealing galaxies with properties that defy past assumptions. This extraordinary surge of early galaxies has ignited a storm of scientific inquiry, challenging experts to reconcile these findings with existing hypotheses. As researchers delve into these mysteries, they are confronted with profound questions about the universe's nature and the forces that shaped its evolution. The James Webb Telescope operates from a vantage point 1.5 million kilometers away from Earth, protected from interference and cooled to near absolute zero. Its design, roughly the size of a tennis court, features a massive primary mirror and highly sensitive instruments. Together, they allow scientists to observe details of the early universe previously hidden from view. This era, known as the Cosmic Dawn, occurred around 200 to 300 million years after the Big Bang. It marks the point at which the first stars and galaxies began to form. The process through which this happened remains the focus of intense research, with hypotheses exploring everything from the influence of dark matter and dark energy to the interaction between star-forming gas and cosmic dust. The telescope's view of galaxies from the cosmic dawn offers a unique chance for cosmologists to test their understanding of these complex elements. By studying these ancient systems, experts can either confirm the accuracy of their current models or uncover flaws that could lead to major new revelations. Originally, scientists expected the telescope to observe only a few faint and small galaxies during its pilot studies. However, reality has surpassed these expectations. Early images revealed a rich array of galaxies with ages, sizes, and brightness levels that challenged all prior predictions. This breathtaking flood of early galaxies has triggered a race among astronomers to set new benchmark records for the earliest known massive systems. New discoveries continue to leave traditional experts awestruck by the James Webb Telescope's revelations. Informed authorities and observers alike have rushed to investigate the presence of these remarkably advanced early galaxies. Some have speculated that errors in the telescope's interpretation of large-scale observations might be responsible for these startling findings. That said, there is broad agreement that these revelations represent a paradigm shift in how we understand the early universe. They offer thrilling glimpses into the possibility of immense cosmic evolution. The new discoveries from the James Webb Space Telescope about galaxies have raised profound questions about the nature of the universe and are testing the assumptions of conventional cosmology, while others continue to determine just how far-reaching these insights might be. As the James Webb Space Telescope, JWST, continues its mission, Its observations are not only challenging the boundaries of current cosmological theories, but also inspiring new lines of inquiry that extend beyond our previous scientific imagination. Each new image, each data set sent back to Earth, adds another piece to the intricate puzzle of the universe's infancy. One of the most revolutionary aspects of the telescope's work is its ability to capture light from objects formed mere hundreds of millions of years after the Big Bang. Light that has been traveling through the cosmos for over 13 billion years. This capability allows scientists to witness the formation and evolution of galaxies in real time, relative to the age of the universe, giving us a kind of cosmic archaeology unmatched by any prior technology. The implications of these discoveries are vast. If galaxies were forming earlier, more rapidly, or with different structures than previously thought, then key elements of our standard cosmological model, such as the rate of cosmic inflation, the timeline of star formation, and even the behavior of dark matter, may require significant revision. Already, alternative theories and models are being proposed. Some researchers suggest that there might have been earlier, unknown physical processes at play in the early universe, perhaps an unknown type of matter or force that accelerated the formation of galaxies. Others believe the discrepancies may lie in how we interpret the telescope's deep-field images and redshift measurements. The debate extends to the nature of the galaxies themselves. Many of the earliest galaxies observed by JWST are far more massive and luminous than expected. This raises questions. How could so much star formation occur so quickly? Were these galaxies enriched with heavier elements earlier than previously assumed? Or is there a fundamental gap in our understanding of early cosmic chemistry? Beyond the formation of galaxies, the James Webb Telescope is also probing the environments around supermassive black holes, quasars, and nebulae with a level of detail never before possible. It is exploring the atmospheres of exoplanets, searching for signs of habitability, or even the faint chemical whispers of life. In doing so, it ties the birth of the universe to the potential future of humanity. Are we alone in this vast, expanding cosmos? Or are we one among many branches of life that have sprung from the same cosmic beginnings? The telescope's journey is far from over. With each orbit, it peels back another layer of the universe's ancient history. Its data sets are massive, requiring years of analysis and interpretation. But what is already clear is that the James Webb Space Telescope is not just observing the universe. It is rewriting our place within it. As researchers continue to mine its findings, we stand on the edge of a new era in astrophysics, one that may redefine not only how we understand the cosmos, but how we understand ourselves. Be reconciled with existing theories. Others suggest that they might be the first signs that the universe is far more complex and puzzling than previously imagined. The crucial question at play is our basic understanding of how the universe we know arose out of primordial chaos. The early discoveries of the JWST could reshape our core ideas about cosmic history, revealing insights not only into distant galaxies and ancient structures, but also into the nature of our very own Milky Way. Mark McFan, senior scientist for science and exploration at the European Space Agency, puts it, "You build these machines not to confirm theories, but to break them. You just have no idea how it will break." The beginnings of the JWST can be traced back to the Space Telescope Science Institute, STSCI, in 1985, even before the Hubble Space Telescope was launched. At the time, the task fell on G. Weir, who was in charge of STSCI, to envision what might come after Hubble. Despite initial doubts, Weir and a small team began laying the groundwork for what would ultimately become the James Webb Space Telescope. Unlike Hubble, which primarily captures visible light, the JWST was made to watch in the infrared spectrum, allowing it to peer much further into the universe. This capability is critical for studying distant galaxies, whose light has been stretched into the infrared due to the expansion of the universe, rendering them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST became the primary instrument for figuring out the mysteries of the universe. The dawn of the JWST's necessity was highlighted in 1995, when the Hubble Deep Field observation revealed countless galaxies in what was once thought to be a blank patch of sky. This discovery illustrated the richness of the early universe and emphasized the need for a telescope capable of probing much deeper into cosmic history. After years of development and a cost of around $10 billion, the JWST was finally launched on December 25, 2021. By July 2022, it was ready to begin its most crucial year of scientific observations. Early initiatives such as the Early Release Science Program and the General Observing Program were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded them. JWST observations have tested existing models of the early universe, revealing galaxies that challenge conventional cosmological assumptions. These astonishing discoveries highlight the importance of pushing the boundaries of scientific inquiry and showcase the unprecedented capabilities of cutting-edge technologies like the James Webb Space Telescope. As scientists continue to analyze JWST data, they might discover additional insights that challenge and expand our understanding of the universe. When the first data began coming in from the JWST, cosmologists eagerly anticipated the results. Many had been preparing their data analysis pipelines for this moment for years. Rather than following the traditional peer review process, which typically takes months, researchers opted to share their findings on preprint servers like AR14, a platform for research papers that have not yet been peer-reviewed. This approach allowed a new kind of peer review to take place through online platforms like Twitter, where established experts could immediately discuss findings. Rohan Nada described this process as science by press release, and the ensuing storm of discussion was both intense and surprising. However, there were concerns about potential drawbacks. Klaus Pontypool, a JWST project researcher at STSCI, warned that while the quick sharing of results facilitated rapid dissemination and discussion, it also carried the risk of overwhelming the scientific process. The rapid release of findings, particularly in such a groundbreaking mission, posed challenges to traditional scientific methods. The general consensus among most specialists is that the current hypothesis of how the universe came to be remains the primary explanation for the early stages of the cosmos. This hypothesis encompasses the development of stars, planets, and life on those planets, including ourselves. The Big Bang, despite the odd name, provides a compelling explanation for what could have happened at the universe's inception. The universe was once densely packed into a space smaller than a pinhead, filled with highly compressed particles. From this moment, a massive explosion of matter and energy occurred, known as the Big Bang. This event, taking place billions of years ago, set the universe's unfolding history into motion. However, as scientific data progresses, it has raised anomalies that challenge the assumptions of this theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever built, scientists believed its observations would support the hypothesis of the universe's beginning. Surprisingly, after just 1 year in space, scientists were astonished by the telescope's capacity to observe so much of the universe's past. The James Webb Space Telescope's extraordinary capabilities have revealed galaxies dating back to a time so ancient that it challenges how we interpret the universe's origins. This revelation has sparked intense examination into what might have existed before the Big Bang. As these early JWST findings ripple through the scientific community, the implications extend beyond astronomy. Philosophers, physicists, and even theologians are beginning to weigh in on the profound questions raised by what the telescope is revealing. If galaxies existed earlier than our models allow, then what forces shaped them? Did the laws of physics behave differently in the first billion years of cosmic history? Could there have been an era before the Big Bang, something we have yet to conceptualize? Some scientists have started to explore alternative theories. One such idea is the cyclic universe model, which proposes that the universe undergoes endless cycles of expansion and contraction, Big Bang followed by Big Crunch, repeating forever. Others propose that our universe is just one of many in a vast multiverse, each with its own physical laws and beginnings. Though these ideas remain speculative, the data from JWST lends weight to questions that were once considered purely theoretical. Meanwhile, the telescope continues to send back data at an unprecedented scale. It is not just peering into the distant past. It is also studying the atmospheres of exoplanets, mapping star formation, and analyzing the composition of ancient cosmic dust. Each of these investigations contributes to a growing mosaic of knowledge that could eventually reframe everything we know about the universe's birth, evolution, and fate. Yet, even as we inch closer to answers, the cosmos continues to guard its deepest secrets. With every new image and spectrum JWST returns, scientists are reminded of how much more there is to learn. The telescope, in all its precision and ambition, does more than look backward. It pushes human curiosity forward, urging us to ask questions we never thought to ask. In this sense, the James Webb Space Telescope is more than a scientific instrument. It is a beacon, one that lights the path into the unknown, where mystery and discovery walk hand in hand.